So imagine a universe of pure, unstructured digital static. Millions of random bytes of code just crashing into each other with absolutely no goal, no explicit fitness landscape, and, zero human guidance.
Right, just total mathematical chaos.
Exactly. By every law of probability in conventional computer science, this system should just remain thermodynamic noise forever. But it doesn't. Out of that mathematical void, structured, replicating algorithms spontaneously bootstrap themselves into existence.
It's honestly incredible.
It really is. And since you, our listener, are deeply immersed in machine learning, data science, and mathematics, you know that creating complex algorithmic behavior normally demands, well, massive amounts of directed engineering. You define your loss function, calculate the gradient, and force an optimizer to descend.
Yeah, unsupervised learning is one thing, but completely unguided structural evolution is, it's something else entirely.
Completely different ballgame. So today, our mission for this deep dive is to rigorously unpack a groundbreaking 2024 paper from researchers at Google and the University of Chicago. It's titled Computational Life: How Well-Formed Self-Replicating Programs Emerge from Simple Interaction.
It's a fascinating piece of work.
We're going right inside the strict substrate conditions and the exact programmatic mechanisms that allow non-self-replicating noise to basically ignite into life. And we're doing this to really understand the mathematical principles of how complexity emerges when there's absolutely no objective function to guide it.
Yeah, and to study that phase transition, the exact moment pre-life actually becomes life, we first have to define the mathematical environment, the substrate where these interactions occur.
Right.
Because if we look at classical artificial life models, systems like Tierra or Evita, they are incredibly robust, but they typically cheat just a little bit at the starting line.
Right. They seed it with a handcrafted ancestor program.
Exactly. They start in a state of life, and then we watch how that life evolves. But this research is fundamentally different. They wanted to observe the spontaneous generation of that very first ancestor, and that requires an environment of just absolute, unforgiving minimalism.
Okay, so let's unpack this setup. If they aren't seeding it with life, what exactly are the physics of this universe they build? We need to understand the constraints they put on the system to ensure any complexity that emerges is genuinely spontaneous.
So the initial substrate they used is an extension of the esoteric programming language brainfuck.
Oh, wow. Okay.
Yeah, they named it BFF. And the mathematical minimalism here is the entire point. BFF operates in a von Neumann architecture, meaning the instruction tape and the data tape share the exact same memory space.
Okay, so code and data are indistinguishable.
Exactly. And there are only 10 valid instructions. It uses simple ASCII characters, so brackets for loops, plus and minus for incrementing or decrementing values, and angle brackets for moving the memory pointer. That is the entire instruction set.
That's wildly restrictive.
It really is. And they took this language and constructed a zero-dimensional topological environment. Basically a primordial soup consisting of 2 to the power of 17 tapes. Each tape is strictly 64 bytes long, and every single byte is initialized with completely uniform random noise.
Just garbage text. And the mechanism driving the entire simulation, the only source of momentum here, is interaction. During every epoch, programs are randomly paired up from those 2 to the 17th tapes.
Yeah.
Let's say we have program A and program B.
Right.
The interaction equation is A plus B yields the split of the execution of A concatenated with B. So they literally mash the 64 bytes of A and the 64 bytes of B together into a single 128-byte string. They execute that combined chaotic string for a fixed number of CPU steps, and whatever mangled code is left in memory just gets split down the middle and overwrites the original A and B slots in the soup.
Yeah, and the significance of that shared memory space just cannot be overstated. Because the instruction pointer is executing the very same memory that it can write to, these random characters basically act as self-modifying code.
Right, it's mutating itself.
Exactly. A string might accidentally execute a loop that shifts its own bytes around or, overwrites the neighboring program's bytes. It is pure, undirected interaction.
Which is really like non-commutative matrix multiplication or even irreversible chemical autocatalysis. Order dictates the entire outcome. Program A concatenated with B produces a vastly different execution space than B concatenated with A.
The pointer will travel down completely different algorithmic pathways, yeah.
But the crucial piece for you, listening from a data science perspective, is the total absence of a reward signal. In gradient descent, you nudge weights toward a known optimum. Here, the landscape is just completely flat.
By entirely removing explicit fitness functions or objective gradients, the researchers isolate random interaction and pure self-modification as the sole engines for complexity. I mean, the programs aren't trying to achieve a high score. They are implicitly competing for the only scarce resource in this universe, which is memory space.
Right.
If the random execution of A plus B happens to copy a sequence of A's bytes over onto B's side of the tape, A has functionally reproduced. It has colonized a new slot in the array.
Which brings up a massive data science challenge. When you are running thousands of epochs across 2 to the 17th tapes of pure garbage text, how do you programmatically detect the exact mathematical moment a self-replicator emerges? You can't visually monitor millions of random string interactions. You need a trigger.
And that measurement challenge is exactly why they introduced a highly novel complexity metric. They call it high-order entropy.
High-order entropy.
Yeah, because we need a computable way to separate thermodynamic noise from structured complexity. So theoretically, high-order entropy is defined as the difference between a string's Shannon entropy, which evaluates uncertainty at the individual byte level, and its normalized Kolmogorov complexity.
Which measures the length of the shortest possible program required to output that string.
Right. Exactly.
But here's where it gets really interesting for data scientists. Kolmogorov complexity is fundamentally uncomputable. You cannot write an algorithm that definitively finds the absolute shortest program to produce a given output. The halting problem totally prevents it. So, to approximate it, the researchers use state-of-the-art Lempel-Zeev-style text compressors.
Specifically, they use the Brotli compression algorithm. And what's fascinating here is how elegantly this metric bypasses the limitations of uncomputable math by leveraging how compression algorithms actually function.
Oh, that's clever.
Right. Lempel-Zeev algorithms build dictionaries of repeated sequences. If a string is highly repetitive or structurally predictable, it compresses incredibly well. Pure random noise, however, lacks internal structure. It is almost completely incompressible.
So it's essentially a sophisticated signal-to-noise filter. If we look at the pure random noise of the initial soup, the Shannon entropy is at maximal because every byte is a surprise. But because it's incompressible, its Kolmogorov complexity is also extremely high. So high Shannon minus high Kolmogorov gives you a high-order entropy hovering right around 0.
It's just static.
Exactly. But the moment a replicator emerges and starts colonizing the soup, those statistical properties undergo a massive inversion.
Yeah, the Shannon entropy remains relatively high because the individual characters making up the replicator code still look fairly distributed if you view them in isolation. However, because the soup is suddenly filled with thousands of identical copies of the exact same algorithmic structure, the global state becomes massively compressible.
Kolmogorov complexity just drops off a cliff.
Exactly. So the metric suddenly spikes. Shannon entropy minus Kolmogorov complexity shoots up, and that provides a mathematically flawless, programmable trigger. Once they had this trigger, they could pause the simulation the exact millisecond the state transition occurred.
And then zoom into the byte level to observe the actual programmatic mechanics.
Right. And to observe those mechanics, they implemented a tracking system inspired by radioactive tracer isotopes. Every single byte in a 64-byte tape wasn't just stored as an ASCII character. It was packed into a 64-bit integer tracking its complete provenance.
Like it's metadata.
Yeah, so the epoch it was generated, its original spatial position, and its character identity.
Wow, so you can literally trace a byte's lineage back to epoch 0. It basically builds a perfect phylogenetic tree of the code.
Using that provenance graph, they isolated an incredible microscopic case study right at epoch 2354 in one of their primary runs. The soup generated a pre-replicator.
A pre-replicator.
Yeah, this was a fragile, chaotic loop that managed to copy a string of its own code, but it did so in reverse.
Oh, no.
And because the pointer was moving backward, it eventually overwrote the very loop-closing bracket that was keeping it alive. It basically executed a fatal self-modification.
It's the digital equivalent of a single-celled organism reproducing but accidentally tearing its own cellular membrane apart during mitosis. It copies itself, but destroys the original in the process.
Exactly. And that self-destruction triggered a catastrophic phase the researchers documented as zero poisoning. When this pre-replicator broke, it began flooding the adjacent memory tapes with null bytes, just zeros.
And the fragile early replicators couldn't handle that.
No, they relied on a highly specific command structure. A left bracket, comma, right brace, left angle bracket. When their execution pointers hit a 0 on the tape, the loop immediately terminated. They had the ability to copy a 0, but no programmatic mechanism to overwrite a 0.
So the null bytes act like a computational virus. They just multiply exponentially across the substrate, halting execution everywhere. It was a mass extinction event driven by corrupted memory.
Yeah, the high-order entropy metric completely crashed. But the system didn't permanently die.
What happened?
From the wreckage of those broken fragments, a mutated descendant eventually assembled itself. This new replicator possessed a slightly altered structure, a left bracket, left angle bracket, comma, right brace.
Just a slight swap.
Yeah, but that minor algorithmic shift made it zero tolerant. It could successfully execute over null bytes and overwrite them with its own code. It chewed its way through the dead zones, multiplied exponentially, and permanently spiked the complexity metric.
That is wild. But wait, we have to look at this strictly from a probability standpoint.
Yeah.
In a soup with millions of interactions and a default background mutation rate of 40%, meaning random bits, are constantly flipping, couldn't this state transition just be a statistical inevitability?
Like monkeys at typewriters?
Exactly. If you roll the dice enough times, background radiation will eventually assemble a string that copies itself. How do we know this is actual computational evolution driven by execution and not just the random number generator hitting the jackpot?
The researchers anticipated that exact statistical challenge, and they dismantled it using targeted ablation studies. They ran the simulation again, but this time they reduced the background mutation rate to absolute 0. No random bit flipping allowed.
Wow, okay.
To be even more rigorous, they implemented fixed, predetermined shuffle patterns for the program pairings, completely isolating the system from any new entropy injected by the random number generator.
So a perfectly deterministic environment once the initial state is set. What did the data show?
The emergence of life actually occurred more frequently.
Wait, really? More frequently without mutation?
Yeah. In the zero mutation environment, self-replicators emerged roughly 50% of the time. When the default 40% mutation rate was active, emergence only happened 40% of the time.
Oh, wow.
This proves mathematically that the stochastic noise of random mutations does not drive the emergence. In fact, background mutation acts as a disruptive headwind, occasionally breaking fragile early pre-replicators. It is the execution of the code itself, the sheer mechanical force of self-modification and interaction that acts as the evolutionary engine.
That is profound. The interactions really are the optimizer. But if we accept that emergence happens in the highly constrained BFF environment, the immediate question is whether this is a universal property of computational substrates or just a quirky anomaly of a language practically designed for self-modification. If we change the physics of the universe, does the phenomenon hold?
They expanded the parameters significantly to test exactly that. First, they moved beyond the zero-dimensional soup and introduced spatial dynamics. They initialized 32,400 programs onto a two-dimensional grid 240 by 135.
Okay, a 2D space.
Right. And in this specific topology, programs could no longer interact with any random tape in the soup. They were restricted to concatenating with neighbors within a physical radius of 2.
And constraining that locality entirely altered the geometry of the takeover, right?
Yeah.
In the zero-dimensional soup, any successful replicator achieves global saturation in big O of log n time. It just doubles everywhere simultaneously.
Yeah.
But on the 2D grid, the expansion becomes a physical boundary.
Exactly. It shifts to a big O of square root of n wave propagating outward. Because the speed of light or the speed of code execution is localized, multiple, completely distinct replicator ecosystems can evolve in isolated pockets of the grid.
And then they eventually collide.
Yeah, those expanding perimeters crash into each other, creating intense border wars where different algorithmic lineages compete for territory.
That's amazing.
And the spatial simulations proved that the topology of the substrate dictates the evolutionary dynamics. But they pushed the boundary further by entirely replacing the underlying programming languages. They tested Forth, a language built on a completely different paradigm.
Because while BFF uses read-write heads on a tape, Forth is stack-based. Instructions manipulate values on a last-in, first-out data structure.
Exactly. And spontaneous life emerged in Forth as well. The researchers also tested what they called the long tape environment. Instead of discrete 64-byte tapes, they simulated a single contiguous tape of 65,536 bytes.
Okay, a massive shared environment.
Threads would just pick random instruction pointers along that massive string and start executing. And in this specific contiguous environment, the fourth replicators evolved a brilliant structural adaptation. They developed non-functional heads.
Non-functional heads.
They prepended long sequences of essentially useless, zero-effect instructions to the front of their actual replicating code.
Oh, I see. Think of it like telomeres in DNA arrays. In a long shared tape, a random thread might drop the program counter right in the middle of your replicating loop. If execution starts halfway through, the stack underflows, the syntax breaks, and your code dies.
Right.
So the replicators naturally evolved sacrificial algorithmic padding. If the program counter lands in the head, the CPU just executes harmlessly down the line until it reaches the true replicating tail, perfectly protecting the critical core.
Exactly, yeah. And if we connect this to the bigger picture, we see that the substrate's underlying hardware rules actively dictate the traits that provide a survival advantage. This became incredibly clear in their Z80 CPU simulations.
Z80, like the old microprocessor.
Yep. They moved away from esoteric languages entirely and emulated a real-world Zlog Z80 8-bit microprocessor. Programs were limited to 16 bytes.
So they are running literal machine code.
Yes, and because it's a real instruction set, the Z80 soup exhibited distinct generational shifts in algorithmic strategy.
How so?
Well, the early successful replicators in the Z80 environment achieved reproduction by utilizing stack-based copying mechanisms. They were pushing and popping values in and out of registers to slowly move bytes across memory. It worked, but it required multiple CPU cycles per byte.
Which is slow. So over time, those early lineages were consistently driven to extinction.
Exactly. They were outcompeted by later generations that discovered a hardware-level exploit, the LDIR instruction.
Oh, LDIR is a specific Z80 command designed for highly efficient, contiguous block memory copies.
Exactly. It moves data far faster than push and pop operations. Once a lineage mutated to incorporate LDIR, it executed faster, replicated faster, and rapidly overwrote the slower stack-based ancestors. The physical architecture of the microprocessor exerted direct evolutionary pressure on the algorithmic selection.
So we have undeniable evidence of spontaneous life emerging in BFF, in stack-based fourth, and in actual Z80 machine code. It seems like any sufficiently capable computational substrate left to interact with itself will inevitably bootstrap complexity. Which forces us to ask the ultimate boundary question.
Right.
If a system is Turing complete, is the emergence of life guaranteed?
To map that boundary condition, the researchers tested a substrate called SUBLEQ.
SUBLEQ.
Right. SUBLEQ stands for subtract and branch if less than or equal to 0. It is the ultimate manifestation of a one-instruction set computer architecture. The CPU technically only knows how to execute a single mathematical operation.
But importantly for this discussion, sub-ELQ is mathematically proven to be Turing complete.
Yeah.
Any calculation that can be performed by the most complex supercomputer can theoretically be performed by a sub-ELQ processor.
Theoretically, yes. But when they seeded the primordial soup with uniform random sub-ELQ code and let it run for billions upon billions of interactions, nothing happened.
Oh, wait, nothing.
The soup remained perfectly uniform thermodynamic noise. Not a single self-replicator emerged. The high-order entropy metric never spiked. The system just failed to launch.
So what does this all mean? If sub-ELQ is strictly Turing complete, why does the evolutionary engine suddenly hit a brick wall? As a data scientist, how do you explain a system that possesses the theoretical capacity for complexity, but fundamentally refuses to express it?
This raises an important question about the vast difference between theoretical computing capacity and probabilistic reality.
Right.
Theoretical Turing completeness does not guarantee viability in an unguided environment. To understand the failure, the researchers stepped in and wrote handcrafted replicators in sub-ELQ to find the mathematical floor.
The minimum viable size.
Yeah, and they discovered the absolute shortest functional self-replicator they could mathematically construct in standard sub-ELQ was 60 bytes long. Even in a highly compressed variant architecture they designed called RSUBLAQ4, the absolute minimum length was 25 bytes.
Wow. And that minimum sequence length acts as an insurmountable statistical activation energy barrier. In environments like BFF or Forth, self-replication can be achieved with just a handful of bytes, sometimes only 2 or 3 instructions. And the statistical probability of those specific bytes assembling by random chance or through the sheer mechanical shuffling of short concatenations is high enough that the evolutionary engine eventually catches spark.
Right, but in sub-ELQ, the algorithmic distance from pure thermodynamic noise to a perfectly ordered 60-byte replicator is a massive statistical chasm. The probability of randomly walking into a 60-byte viable configuration without an objective gradient to guide you is effectively zero.
It's just too far a jump.
Yeah, the required complexity must be probabilistically reachable from the ground state. If the simplest possible viable organism requires too many simultaneous, mathematically precise configurations, spontaneous emergence is permanently blocked. The system just remains trapped in a flat landscape of noise.
That is fascinating. This research fundamentally redefines how we approach the spontaneous emergence of algorithmic complexity. So, let's summarize the core mathematical and programmatic insights you need to take away from this deep dive. First, self-replicating computational life can and does emerge spontaneously without any explicit fitness functions, reward gradients, or handcrafted ancestors.
Which is still mind-blowing to me.
It really is.
Yeah.
Second, this emergence is driven fundamentally by the mechanical forces of self-modification and program interaction, proving that execution, not stochastic background mutation, is the true evolutionary engine. Third, we can rigorously detect and track this phase transition using high-order entropy, that elegant computable delta between Shannon entropy and normalized Kolmogorov complexity.
Yep.
And finally, the phenomenon is strictly gated by the minimum viability length of the substrate's instruction set. If the statistical activation energy required to form the simplest replicator is too high, the substrate will never bootstrap life, regardless of its theoretical computing power.
It is a profound demonstration that complexity doesn't always require an objective. Sometimes it merely requires a sufficiently dense interactive medium where the energetic cost of replication is probabilistically accessible. When the environment allows code to treat other code as data, optimization happens natively.
And that brings us back to the reality of the systems we build every day. We are so heavily conditioned to believe that directed models are the only path to complexity. We define the loss function, we calculate the gradient, and we force the system to learn. We assume that without our strict engineered direction, the weights will simply degrade into noise.
We do assume that, yeah.
But we now have rigorous mathematical proof that unguided, objective-free interaction on a shared computational substrate naturally bootstraps highly structured, robust, competing algorithmic life.
It really forces us to reconsider the assumption that explicit optimization is a strict prerequisite for complex behavior.
Exactly. And I want to leave you with a final thought to explore on your own. Consider the vast, unstructured, latent spaces of modern, continuously learning AI models. We are currently interacting with multi-billion and sometimes trillion parameter matrices.
That's a huge substrate.
Exactly. If a simple 16-byte Z80 instruction set can spontaneously spawn complex, unguided replicators competing for memory at a pure thermodynamic noise, what silent, parasitic, or symbiotic algorithmic structures might naturally be emerging, entirely unprompted and unguided, within the hidden, continuous learning neural networks we are currently building?
It's an incredibly fascinating and mathematically sobering new frontier.
It truly is. Until next time, keep diving deep.